过不了，不过我们后面的后按点可以接上。
哦，那我把这个到哪？
你给我往里倒，都到。
这能带上飞机吗？
这应该可以吧。
身份证还用吗？都？
身份证和登机牌关起来要用。
It doesn't matter, not in basketball.
And test only those pairs for similarity. By doing so,
Hello, everybody. Welcome back. I know you missed me. So today we're going to continue on our frequent item set lecture. We're going to finish that frequent item set lecture, and then we are going to talk about something very interesting. So your assignment 1 was due yesterday. Your assignment 2 is announced on Blackboard. So make sure you start early, use your office hours. Any questions before we start? No? Okay. All right, so one of the algorithms that we haven't covered in finding frequent item sets and also a priority-based algorithm is the Toivonen algorithm. So what exactly is Toivonen algorithm? Remember, a priori, PCY, multi-hash, multi-stage, we run one pass over the data and we collect some filters, we build some filters, and we use the filter in the last pass to help us to minimize the number of counters we have to initiate, right? And in the limited pass algorithms, sampling, we just take a small sample, Sun algorithm, we split the data into multiple sets, and then we do the frequent item set. Good. In Toivonen's algorithm, we want to be able to also build a filter. Well, it's actually not a filter, an indicator. And what the indicator does is it will be able to tell us if we will have false negative. So let's look at here. given sufficient amount of your memory, we want to be able to use one pass over some small sample data and one full pass over the entire data set. So still remember, this is very similar to your sampling approach, right? So in the sampling approach to find frequent item set, what would be the problem? Well, we know that we might want to use a small support threshold, but you will always have false positives and false negatives, right? So just a recap, what exactly are false positives? Anybody?
It will be the frequent item sets in the small sample, but actually it does not in the whole data.
Great, cool. So this means we say it's frequent, but it's actually not in the entire data set. And frequent false negatives means we say it's not frequent. We say, okay, not frequent, but it's actually frequent in the entire data set, okay? And what do we do in the sampling approach to help us eliminate some of this? Well, we run again a full pass over the entire data set. We take all the positives and we count them, because now we only have a small set of positives, identified frequent item sets. So we are able to do this. And we are able to remove false positives, but we cannot really remove false negatives, okay? The Toivonen algorithm will help us eliminate both of this. So it will give us no false positives or negatives. However, there is a small chance that the algorithm will fail to produce an answer. This means it will not identify frequent item set. Your indicator will say, oh, something is wrong, you have to rerun it again. Then you rerun it again with a different sample, see if it will work. And if this time the indicator said you pass, you pass, okay? So if it failed, you have to repeat the entire process again with a different sample until it gives you an answer. But in general, it only needs a small number of iterations. That means this repeat, run it again, repeat, is unlikely to happen. So let's look at the algorithm. In the algorithm, we first find candidate frequent item sets from the sample, exactly like what you did in the sampling approach. You start as in the random sampling algorithm, but you lower the support threshold so that you will reduce the possibility to have false negatives, right? So for example, if the sample is 1%, we use this number as the support threshold so that you have less false negatives. However, in this case, you will also have higher false positives. But our goal here is to avoid missing any item sets that are frequent in the entire basket. So we want to avoid this. So think about this. Why do we want to avoid this, but at the same time, taking the risk that your false positives might increase? Anybody?
Is that because we want to find the frequent item sets?
Yeah, we want to find frequent item sets, but remember when you use a smaller support threshold, you minimize false negatives, but you also increase false positives. Why is this okay? Why is it increasing false positives okay?
Because we are running a full pass later. So
yes.
Yeah.
Great. Because we are going to run it again. So in the second pass, we will be able to eliminate this, right? No matter how many false positives we have. Thank you. So we know that the smaller the threshold, the more memory is needed to count all candidate item sets, because now you will have many candidate item sets, but less likely the algorithm will not find the answer. So the success rate is higher because you have less false negatives. So how does it work? Let's look at the algorithm. After we find the frequent item sets from the sample, we want to construct something called the negative border. The negative border is actually just a set of items. This is a collection of item sets that are not frequent in a sample, but all of their immediate subsets are frequent. So what does this mean? So in the sample, they are not frequent. So sample tells you they are not frequent. However, you have some other evidence here. All of their subsets, immediate subsets are frequent, so they could be frequent, right? So these are the things that we are not entirely sure. And the immediate subset, the definition of the immediate subsets is just constructed by deleting exactly one item from an item set. I'll show you a couple of examples. So for example, if you're ABCD, if this item set is in your negative border, that means it's not frequent in the sample. Okay, so we know this. Also, if you delete any of the item here, so you delete D, you got ABC, you delete A, you got BCD, and so on. If all of them are frequent. Okay, so this tells you that ABCD might be frequent, but your sample tells you it's not frequent. So we put it in the negative border. How about single items? For single items, A, this item is in the negative border if and only if it's not frequent in the sample. So any single items that are not frequent will be in your negative border. So conceptually, it looks like this. You have lots of item sets, and this is your frequent item sets, and these item sets are in your negative borders. They're the immediate neighbor of all your identified frequent item set. So if you have false negatives, they are here, right? They're most likely to be here. So the algorithm first pass will find the candidate frequent item sets from the sample, exactly the same like what we did in the sampling process. Identify the item sets that are frequent for the sample, and you construct the negative borders. Okay, so these are the item sets that are not frequent in the sample, but in all of their immediate subsets are frequent. Great. Now you have negative borders. First pass. So what do you do in the second pass? Well, second pass, we know that, second pass, you have to process the entire file. We know that we want to eliminate false positives, right? So you have to count this. Candidate frequent item sets from the first pass, because the candidate contains true positives, which means they are truly frequent, and false positives, the ones that are only frequent in the sample. So by counting them, we are able to remove this. And we want to count all item sets on the negative border. So this tells us, this serves as an indicator of false negatives. There will be two cases. The first case is no item sets from the negative border turns out to be frequent in the entire data set. So we are good, right? This means we will not have any false negatives. We identify everything here. Second case, some member of the negative border is frequent in the entire data set. That means we do have false negatives. We cannot really give an exact answer, and you have to run it again. Okay. So for the Toivonen algorithm, in summary, our goal is to save time by looking at the sample on the first pass. And we know that by looking at sample, we will have false negatives and false positives. So two steps to eliminate false negatives. First, we build the negative border, serve as an indicator. Second, we lower our support threshold, so the chance that we are going to have false negatives will be smaller. Okay. To remove false positives in the second step, second pass, we will count everything that are identified as frequent item sets and remove this. So if some members of the negative border is frequent in the entire data set, we cannot be sure. it could be some of the even larger item sets that are neither in the negative border or in the collection of the frequent item sets for the sample, but are frequent in the entire data set. Let me show you this. So for example, if we do have A, B, C that are not frequent, but all the immediate subsets are frequent. A, C. Okay. Frequent, frequent, frequent. And we add this into the negative border. Are we good so far? Yes? Okay. So in the second step, what are the things we have to count? Let me use the whiteboard. Okay, think about this. So if you run an algorithm, you're pass one. Pass one, you take a small sample and you run your priori PCY any algorithms to find frequent item set, and you identify some item sets, frequent item set candidates. Okay, so let's say you have IS1, IS2. So these are your candidate. And we know because we are only processing the sample, so this will contain false positives and false negatives. Okay. In order to minimize this, we use a small support threshold. And in order to eliminate this, we are going to run a second pass. Second pass, this memory space is going to store your item set candidate. And based on that, you start to count, right? You read your data set again. And let's say in this case, if you have A, B, C is in your negative border, AB is frequent, BC is frequent, AC is frequent. Okay, because you count it again, you are sure. You are exactly sure. How about ABC? Well, ABC was not in here. Was not in here. So it's in the frequent, it's in the negative border. And when you count it again in the second pass, you say, hey, ABC is frequent now. So can we just add ABC into the final result and say we're done? Will there be other false negatives that we have not identified yet? Anybody? Did I just confuse everybody? Let's say you have A, B, C, D as your single items. Okay, you only have A, B, C, D. First pass, you identify A as frequent, B as frequent, C as frequent. And you say AB is frequent. What else? AC is frequent, and so on. Okay, so you have larger frequent item set. Frequent item set from sample. Are we good so far with this second example? Can I have some response? Okay, good. All right. So we know in this set, you will have false negatives and false positives, right? Because you're calculating this from the sample. That's good. So in order to remove false positives that we all know, right? Because the second pass you're going to count exactly how many times they appear in the entire file. So let's say entire file appear 30 times, 40 times, 50 times, 60 times, 30 times. And let's say your support threshold is exactly 40. What are the item sets that are your false positives, and you can remove them based on this example? This is your support threshold. You can remove A. What else can you remove? A, C. Okay, bad example because AB cannot be used. And AB. Okay. All right. So A, AB, and AC. Because AB here is 30 as well. Great, you remove false positives. I think right now, one of the concern is still the false positives, false negatives, right? So how do we look at this? If we want to construct a negative border, we have ABC. And if we will only look at single items, who would be in your negative border? Which item set is not frequent in the sample, but all the immediate items are frequent? No, A is frequent in the sample, right? Let's look at single items. Okay, great, look. D will be in your frequent, in your negative border. Negative border, D. Which means in your second pass, you have to count how many times D occurs, right? Remember we said in your second pass for the algorithm, you have to count all the frequent item set candidate, and you have to count all the negative borders, okay? I'm ignoring all this other stuff. I'm just focusing on single items now. There might be other things that should be in the negative border, but I didn't list here, okay? So let's just look at D. So in the second pass, you count all this and you remove the false positives, great. And you count this, and then it turns out your D has a count of 50. What does this tell you? Is D frequent? Is D a frequent single? Yes, D is a frequent single, right? So then you have two options. The first option is, how about let's just take D and add it to the final list of frequent item sets, and we're done. Does that help us to eliminate all the false negatives? So people are saying no. Why? What could be other false negatives here? Remember, after we remove the false positives, these are not frequent anymore. And after we count the negative border, now these are our new these are our new frequent item sets. All right, so Lini has a good answer because BD could be frequent now, right? D is frequent, B is frequent, BD could be frequent, but in our previous example, could BD ever be in your frequent item set candidate? Can you find BD here in this list? No. Why is that? Well, because in your a priori-based algorithm, if you already know D is not frequent, you will never generate a counter for BD, right? You assume BD is not frequent, so you were not going to generate a counter for BD, so you will never be able to count it. So we don't even know if BD is frequent or not. The only thing we know that is D is frequent, so there are possibilities that either BD could be frequent or CD could be frequent, or even BCD could be frequent that we ignored in the original list. And this tells you that you have to rerun your algorithm again, maybe with a different sample or a smaller support threshold. And next time, hopefully, all the negative border will turn out to be negative, means infrequent, and then you're good. So there's a question. If D didn't show up in the sample data sets, how would you know to see if is in the negative border. D is in the sample data set. D is not in the result, the frequent item set result from the sample data set. D is here. This is your sample.
Can you talk about how to distinguish a negative border?
So negative borders are the item sets that are frequent. Sorry. Let's talk about D, since we like D very much. This is your original file. You take a small sample and you run the priori. Let's say you run PC1, okay? And in the small sample, this small sample will cover A, B, C, D. Let's say you only have 4 types of items, okay? It's a sample, it should cover, a good sample should cover every item types you have in the entire data set. After you run PCY, you have some frequent item set candidate. Okay, and this only has A, B, C, and some other pairs or triples. Yeah, so it's highly unlikely that your sample will not cover some item sets. Just think about this. If you take 10% of the sample and your sample does not cover D, that means D might not be even frequent, right? You don't really have to care about D because it just appear infrequently. Okay, so this is your frequent item set candidate. And to find your negative border, you just look at all your frequent item set candidate and you say, hey, who is not frequent, but all the immediate subsets are frequent. So you start from a single items. Now we are looking at A is frequent, B is frequent, C is frequent, D is not frequent, right? So D will be in your negative border for single items. Then you look at pairs. You say, all right, A, B is frequent, good. What are the pairs that are not frequent? So B, C are not frequent, but B is frequent and C is frequent. So good, B, C will be in your negative border, right? And so on. So you look at all the item sets that are not frequent in the sample, so not here, but all the immediate subsets are frequent. Then that's your frequent. That's your negative border. All right, I hope this helps. It's very simple. You just need to think about, I think one of the things that really get confused easily is the negative border. The goal to have the negative border is to use it as an indicator to tell us if we have negative, false negative or not. The goal of the negative border is not to help us capture all the false negatives, right? Because we cannot really do it unless we count everything we can. All right, let's go back to the slides. Okay, so I hope you like all the priori-based algorithms. And the next algorithm we're going to talk about is FP growth. It's a very cool algorithm. And what I want to say here is this is our original TA, Yijin. So one day Yijin said, why don't we teach FP growth? It's a popular algorithm for finding frequent item set. And since this is probably the last semester, we are teaching data mining at USC. Well, I am teaching data mining at USC. So I added this component to help you. And we also add this component into your assignment too. And you will be able to see how you would use MLlib, Spark MLlib to find frequent item set and compare that with a priori. All right, so what is FP growth? remember all the a priori-based algorithm we talk about. So a priori, PCY, multi-stage, multi-hash, and what else? Toivonen and Sun algorithm. These are all a priori-based. That means we were generating some candidate item sets. Then we test them to see if they are frequent, right? And our goal is to have very small candidate item sets so that when we test them, we are able to put everything in the main memory. But all these approaches are really computational expensive, IO expensive. Remember, if you want to identify pairs, you have to read it twice. If you have to identify triples, you have to read it 3 times, right? FP growth algorithm overcome this problem by allowing frequent item set discovery without really generating candidate item sets. It's a 2-step approach. That means you still have to have 2 passes. First pass, or first step, you build a tree. It's a compact data structure. We call it FP tree. I think this is frequent pattern tree. So FP tree, it requires 2 passes over the entire data set to build. Now, since this is a compact data structure, you can store the entire data set in memory. Then you can process the tree to extract frequent item set directly. And this is based on recursively traverse through the entire tree. So let's look at the entire algorithm. Step 1. Step 1 of the FP tree construction, we are going to construct a FP tree with 2 passes over the entire data set. So remember, now we are not going to focus on only pairs. These 2 passes will generate a compact structure, and we are going to use the compact structure to identify all kinds of frequent item set. The goal is to use minimum memory to store the tree. So we have to design this tree in a very smart way. At the same time, we want to preserve the frequent patterns in the tree. So how do we do this? Pass 1. We scan the entire data set and find support for single items. Okay, so focus on single items first, right? Remember, this is very similar to what you did in a priori. You scan the entire file and you use this part of the memory to count single items. Then you throw away infrequent single items. Great, like we did before. You sort frequent single items in decreasing order based on their support. And we're going to talk about why this is important, but sort them based on their support. So intuitively, the single items that have high support are highly likely to be a frequent item, to be in a frequent item set, right? So we want them to be at the front. Then we use this order to build the FP tree. And because we are using this order based on the support, so many prefix can be shared, and that will give us very small memory footprints. And I'm going to talk about what does it mean common prefix can be shared. So here's a running example, and you can also look at this website. They have some explanation of this algorithm. So say you have 5 transactions. These are all the item sets you have, the transactions, right? Like market basket model. This is your basket, 5 baskets, some items. Pass number 1. Based on your file, you count single items. These are all the items you have, and these are your frequencies or support. Okay, so based on the support, let's say your support threshold equal to 3. You eliminate the infrequent single items and you order the remaining ones by the support. So this is new information you obtained from your first pass. You only need this. So what does it mean? K equal to 5? 1, 2, 3, 4, 5. E equal to 4. 1, 2, 3, 4. Right? What else? Do we have I? Okay. I only 1 time. Frequency 1, so it's not frequent. We don't need. All right. So this is our result from your pass 1. Great. Pass 2, now we want to construct the tree. So every node in your tree will correspond to single items, and they are going to have a counter. So this is the basics that you have to know about this tree. FP graph algorithm will read one transaction at a time, read one basket at a time, and map that basket into a path in the tree. And the way we map it, so think about this. Let's say you have a basket, A, B, C, and they're all frequent. What are the different types of paths that you can generate? You can generate A to B to C, right? Or you can generate B to A to C. It doesn't really matter because this is a set. You can rearrange the order. However, in generate an FP tree, we want many of these paths to share the same prefix. If I give you a second example, B, C, D, A, second basket. We want these two baskets to share the same path. That means their order should be similar. So that's why we're going to use a fixed order to order all the items in the basket so that the paths can overlap when transactions share items. And we're going to see some examples. So if you're not clear about this, you're okay. In this case, we are going to use the counters to increment the counters to indicate how many paths go through a node, and popular single items will be the shared prefix, right? Let's look at some examples. Say these are all your transactions. After we identify first pass, these are all the frequent single items. We can rearrange your basket, right? So why do we have KEMOY? Well, KEMOY, that means we do not have N, because if you look at here, N is not frequent. Cool. And why do we have K as the first item? Well, because K has the largest support, right? The most popular item here. If you look at your T2, DEKNOY, first you remove the infrequent ones. Which one? And again, you have EKOY. So based on the support, K has 5. So first, put K here. Then E is 4, put E here. And you have O, you have Y. Okay. So if there is a tie, you break the tie in an arbitrary way, but it's deterministic. That means if next time you see O and Y, you want to break this tie, and here you put O first, the next time you want to put O first. But it doesn't really matter. You can start by putting Y first, but every time you have to put Y first, okay? That means deterministic. So question? Okay. All right, so second pass, you read the item, you read the basket, you remove the non-frequent one, you order them, then you start to create a tree. So now you can start to see what we mean by overlapping paths. So the tree has a root of null. This means an empty basket. Then you start to insert each basket. So first one, you already reorganize them. So it's KEMOY, okay? So it's a path. And look at here, the most popular one is here, K, because we expect that next time when you start to insert something, you will see K here as well, then they can share. For example, here. So look at the basket here, the ordered one. After you insert the first one, now you insert the second one. So second one is KEOY. So K, we already have K. So incremented means now this path has K twice. E, this path has E twice. But the third item is O, and this is M, which is okay. We just create a new branch and we say O, 1. And the last item is Y and Y1. Great, you just inserted the second basket. And just keep a note here, we have all this dashed line here. This is just a link in memory so that we can traverse from this node to this node very easily without traversing the entire tree, okay? All right, great. So pointers are maintained between nodes containing the same items, like here and here. Well, yeah, it's similar to trees. The more paths that overlap, the higher the compression, because see, instead of creating another K and E, we are using the same path here, right? So the more paths that overlaps, the higher the compression, and your FP tree may fit in memory. The dotted line is not bidirectional. That's a good question. I don't think it's bidirectional, but it can be bidirectional. Depends on your tree search algorithm. We're going to look at some of this search later. All right, so next basket, KEM. So this is your tree after you insert 1 and 2. When you insert the third one, you insert K. All right, we have K, so increment it. You have E, you increment it. You have M, you increment it. Okay, so KEM. Next one, KMY and KEO, you do the same thing, and this is your final tree. All right, cool. So what have we learned here? Well, now we have one tree to represent the entire data set instead of storing the entire data set in the memory, right? And we hope this tree is compact. That means many of them are going to share the same path, so this number should be large. Now, what we want to do next is just to traverse this tree to be able to find all the frequent item sets, and we are done. So let's look at the tree size. This FP tree usually have a smaller size than the uncompressed data. Well, we say uncompressed, this is the raw data set. Typically, this is because typically many transactions share items so that they share this prefix or the path going into the leaf node. The best case scenario is all transactions contain the same sets of items. Everyone share the same path, so you have one path in the FP tree. Worst case scenario, every transaction has their own unique set of items. There's no shared path. So that in this case, your FP tree is at least as large as the original data. However, your storage requirement for the FP tree will be higher because you will need to store the pointer. Okay, but this is highly unlikely to happen because many of the paths will share prefix. The size of the FP tree depends on how the items are ordered. Why? Anyone would be able to answer this question? Well, the order of the items in a basket determines how many prefixes can be shared, right? So not how many prefixes are, so how many prefixes can be shared. And if you have many prefixes that are shared, then the best case scenario, you have one path. Ordered by this decreasing support like we did in the example is typically used, but it does not always lead to the smallest tree. That means no one has proved this. It's just a heuristic. It works well in practice. So step 2 is now we want to look at the tree and generate frequent item sets. So in this case, we are going to talk about this FP growth algorithm. And this is a bottom-up approach. That means we are going to start from the leaves toward the root, divide and conquer, look at E, determine if E is frequent, then look at DE, AE, and all that, and all these different things, okay? So the first step is to extract prefix subtrees ending in item sets. For example, let's say this is your tree, your FP tree. If we want to start from E, we will extract a tree like this. So look at the difference. It's very simple, right? You just take all the paths that will lead to E and ignore all other paths. And here you can see why we will need all these links, because it will help you to traverse the tree very easily. And this is the tree, contains D, and so on. Once we have the subtree, each prefix subtree is processed recursively to extract frequent item sets. Then you merge all the solutions. Then you call it a day. You say, I find all the frequent item sets. So it's very simple. You start from E, D, E, C, E, and so on. But let's look at one example on how exactly this traverse works. So this is your FP tree, okay? Based on all your items, we now order them starting from the least support. And we say we want to look at this Y tree. Okay, so Y tree. But when you implement the code, you actually do not just remove the tree. It's just the way you traverse the tree. So let's look at Y tree. We start by generating this conditional pattern base from Y. We say, all right, who would lead to Y? Well, you have K, E, M, O, right, from root. So one path. How do we know this is one path? Well, because Y has a counter of 1. That means this path only goes to Y once. So that's here, KEMO. And what does it mean in terms of your basket? Well, that means you find KEMOY in a basket, right? That's how you insert them into this tree. What would be the next one? Well, you have KEO. Why do we have KEO? Now, KEOY, okay? And also ones, because you have a 1 here. KEO. Do we have other Ys? Other path ends at Y. Okay, all right, Y, great. KM, and only once. Now we finish Y, we look at O, who ends at O. Now K, E, M, O, once. So KEM. Other path, K, E, O, okay, great. KE, but now we have a 2, right? Because here you have a 2, that means some baskets contains KEO at least twice, right? We don't, well, from the tree, we don't really know if it is KEOY or just KEO, but we know at least you have KEO twice. M, KEM, so 2, KE, and what else? K to M, so K to M once. E, K to E 4 times, right? Because E has 4. And that's it. We don't count K because it's starting from null. Okay, so this is your conditional pattern base. And based on this conditional pattern base, what we can do is we can generate these frequent pattern trees. Remember our support is 3. So if you look at this pattern, what does it tell you? So it tells you that Y was in a basket with KEMO once. Okay. Y was in a basket with KEO once. Y was in a basket with KM once. So what would be your frequent pattern tree? K, 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 3 times. I think our support is 3. Right. Good. What about others? E, will E be your conditional frequent pattern, which means E and Y could be frequent? No, because E has 1 and E has 1, so EY is 2, right? What else? M? No, because M is 1, M is 1, O is 1, O is 1, so O is 2. So, okay, we can only get K. Let's look at the second one. KEM 1 and KE 2. Oh, great. So KE is here once and KE is here again twice. So we know at least KE has occurrence or support of 3. How about M? Well, M is only here with a 1. So either KEM and O or MO will not work, right? So KE. Let's look at M. KE, 2, K, 1. So 2 plus 1 is 3. So K is 3, and you don't have E because 2 is smaller than your support threshold. The last one, E and K has 4. So K equal to 4. Great. So what does this mean? Based on all these items, based on all these single items, these are your conditional frequent pattern tree that will be able to help you to generate your final answer. So these are only candidates that can be work together with the single items to generate frequent item sets. So how do we generate it? Look at first one, you have K, right? And your item is Y. So your frequent pattern generated will be KY together with the support 3. The second one, you have KE, you have O. So what are the types of frequent items you can generate? You can generate K, O, right? And the count is 3. Or you can have E and O, or you can have EKO. So question, why KE is not 4? Because 1 plus 2 is 3. M, K is 3. So M and K will be your frequent item sets with the support equal to 3. E has K, so EK is 3. This should be 4. Okay, that's it. M also, of course, plus your frequent single items. And these are all the frequent patterns that you can identify. Okay, just based on the tree. So let's look at this algorithm. The advantage of your FP growth algorithm is it requires only 2 passes over the entire data sets. And these 2 passes is focusing on generate FP tree, which is a compressed data set of your original raw transactions. You do not really generate candidates, right? We do not generate candidates, and it's much faster than a priori because you can count, traverse the trees all in memory. It's much faster. The disadvantage of your FP growth algorithm is the tree might not be able to fit in memory, and it's expensive to build because you have to insert it and all that. There are algorithms that you can speed up this recursion process, but still, if it's too big, it is too big. So some additional readings, if you're interested, read this paper about the complexity. Also, watch this YouTube video, you will be able to see how they process this transaction to generate the FP tree and find the patterns. Even if you don't watch it, I want you to try this sample by on your own with the support threshold equal to 2. See how you will be able to build a tree, find the patterns, and identify frequent item sets. All right, so that's everything I want to tell you about frequent item sets. On the slides, there are something about hashing you should read if you're not clear about hashing, but that's it. We're going to take a break for 10 minutes, come back at 7:05. If you have questions, leave it in the chat. I will answer them when I come back. Oh, before we go, your assignment 2 will be implementing frequent item set algorithms, right? You are starting by working on a smaller sample data. Then you work on a larger also simple data, but you're going to use a priori or PCY with the Sun algorithm. Okay, that's good. I think that you know how to do it. Then you're going to try this FP growth algorithm by calling the MLlib package from Spark. This gives you a chance to play with the machine learning libraries in Spark. And also, if you have more time, you want to implement the FP growth algorithm by yourself, we will give you bonus scores. So make sure you read your assignment too. Start early, go to your office hours, and I will see you in 10 minutes. All right, I'm back. So if you ever have to answer FP growth questions during your interview and you find the lecture useful, send an email to Thinker. All right. Now we are going to talk about our topic for this and next week. It's finding similar items. All right, so in these 2 weeks, we are going to cover everything here. I'm going to tell you the problem, tell you the application. Most importantly, we are going to focus on 2 algorithms, the mean hash and the locality sensitive hash. These are 2 very, very cool algorithms, and you are going to use them to build your recommendation systems for your assignment 3 and the final project. Oh, okay, yeah. All right, let me upload the slides. Good call. All right, it's on Piazza. Okay, so what is the problem? Let's say we have lots of items. These items are represented as a set of objects. You can think of these items are what we called basket in the previous lecture, and the object here is actually our items in the previous lecture. Okay, might be confusing. The problem becomes we want to be able to find similar sets, but the challenge is you do have large sets and you have large numbers of items or sets. Okay. What are the similarity measurement that we can use to measure sets? So I don't think we have talked about this. This is a very important similarity matrix in data mining or in many machine learning applications as well, called Jaccard similarity. You're going to see Jaccard similarity many, many times in this course. So the way we compute Jaccard similarity is we calculate the size of the intersection divided by the size of union. So Jaccard similarity, based on this definition, you know that it works on sets. So Jaccard similarity between set S and set T is like this. So what's the intersection? Here, 3. How about union? One, 2, 3, 4, 5, 6, 7, 8. 8. Great. So this is the Jaccard similarity between these 2 sets, right? Intuitively, you're looking at the intersection over union. It's pretty common in many applications. So how do we use this? Let's say we want to be able to find similar buyers, and these are all our buyers, and these are the item sets the buyers has bought. So B1 bought A and B, B2 bought A, B, D, B3 bought A, C, D. What's the Jaccard similarity between B1 and B2? B1 and B2 intersection is what? What is the intersection between B1 and B2? Anyone? A and B, great. So 2, what's the union? A, B, and D. Awesome. So we do the same thing for B1 and B3. Now we know B1 is more similar to B2 than to B3. Okay. So who's most similar to B2? Well, B2 more similar to B1 because, and also B2 also B2 bought D, we will be able to recommend D to B1, right? This is buyer to item recommendation. If you look at here, let's say you only have 3 users. These are all their the items that they have purchased, or the records you know about all these users. And now we are looking at B1. We want to recommend items to B1. So based on their purchasing history, we first identify the most similar users to B1. And in this case, the most similar user is B2, right? Not B3, because the Jakarta similarity between B3 and B1 is what? What's the intersection? I will answer the question next, but let's look at this first. What's the intersection between AB and ACD? 1. What's the union? A, B, C, and D, right? 1/4. Right here. So we know B2 is more similar to B1 than B3, so we don't like B3. Then we look at this purchasing history. We say, oh, B1 has not purchased D yet, so let's just recommend this to B1, okay? And we can do the same thing if you have large data sets. So there's some question, let me see. So the question is why it's 3, not 5? I guess you're talking about the union between B1 and B2. So the union between B1 and B2 is ABD, so that's 3. The book said it was the sum of the size. No, I don't think the book says that. Sets are unique items, correct? So you want to eliminate the duplicates, okay? All right, so find similar buyers could be one potential applications that you can use to compare different sets, right? So this is a set, this is a set, this is a set. And we can treat buyers as a set, or we can treat items as a set, right? If you look at here, A has been purchased by B1, B2, B3, right? A, and B has been purchased by B1 and B2, B1 and B2, B. And then if you compare all these sets, you will be able to find similar items. So let's think about this problem. So to be able to find the most similar items to A, what are the things we need to do, given that you have A, B, C, D? What's your tool? Well, you have Jakarta similarity, right? So when we say most similar items to A, that means we're going to do comparison between AB, AC, and AD. Then we pick the largest similarity to identify the most similar items, okay? So this sounds very easy, but if you have a really large data set, you might have 1 billion items, and then you have to go through this for 1 billion times. It's very time consuming. Or if you have many items in here, or many buyers, this basket becomes really large. So compare AB will take a lot of time. So we don't want this, and we don't want this, right? So how do we solve this problem of large data set? Well, how about let's look at this problem as a frequent item set problem. Say if we want to find similar items, we say items purchased together by many users. They might be similar, yes. Users will be the transactions, similar items will be the frequent item pairs. Good. And if we formulate the problem as a frequent item set, but we put the basket as the items, then we will be able to find similar users, right? Remember this market basket model? We are looking for similarities, relationships between items. So in this case, your basket should be your items, and your items should be your buyers, because we are looking for similar buyers or users, okay? So with this work, let's look at one example. Based on your transaction data, let's say we use a priori, minimum support equal to 2. You start by counting the support of single items. You prune your search space, and you generate candidates of pairs, and then you count them here. Sorry. Use minimum support equal to 2. This is your final result. Great. Would there be a problem of this approach? Well, there is a problem, or we will not have to go through this week on similar item sets, right? So potential problems. Are buyers B1 and B2 still similar? Well, if you look at here, intuitively, they are pretty similar, right? Their Jacquard similarity is what? 2/3. Okay. But if we are using a priori to help us identify similar buyers, what would be your basket? Anybody? What would be your basket using a priori? Basket items. Remember, we are looking for a priori. We are looking for a relationship between items. So your items should be B1, B2, B3, and so on, okay? And your basket is the items here. That would be A, B, C, and D, right? So if we want to use a priori, the problem becomes, all right, you have basket A, contains what? B1, B2, anything else? B3, great. Right, because A is in B1, B2, and B3. How about your basket B? Contains B1 and B2. That's it. So would your a priori identify B1, B2 as a frequent pair? Well, it will not, because B1 and B2 only appear in how many baskets? They will appear together in the basket A and in the basket B, right? So their support is only 2. And even if when you are looking at this number of baskets, you have 9 baskets, 2 is still very small. Not to say if you have millions of baskets, support equal to 2 will never be able to, you will never use support equal to 2 to identify frequent pairs. So B1, B2 will never be frequent pair given the support threshold that you would use. But they're still similar, right? Because when we look at them, their Jacquard similarity is high. So we cannot really use a priori, because a priori is going to help us find common events given the entire basket file. And similarity is actually local. We're looking at 2 things and we want to compute their similarity. We don't really care about all other people. So how do we solve this problem? Before we talk about the algorithm, let's look at another application. And we are going to use this application throughout these 2 algorithms to show you how we can use the similar item sets algorithm to find similar documents. So the application is to find similar web pages, and could be documents. And the way we define similarity is near duplicate. That means we can identify plagiarism, mirror pages, news from the same AP, many words are similar. So can we use a priori? Well, if we're using a priori like what we did in our frequent item set example, your web page is a set of words or sentences. Then your baskets becomes word and sentences. Your items becomes web pages, right? Because finding similar web pages, relationships between pages, relationship between items is the goal for a priori. So that's how you set it up. But what would be the problem? The problem is exactly what we saw before, low support, but still similar because a priori work on global data set, similarity is local. Word as baskets could be too fine, sentences could be too coarse. So how do we decide? Well, let's solve one problem. Let's solve this problem first. We can look at web pages as a set of shingles, like shingles. What does it mean, shingles? Well, it's actually just a string of characters. A shingle is a subsequence of k characters. And this k is a hyperparameter. That means we can set whatever k we like. Let's say if your web page is this string, okay, because you can convert any web page into one large string. And if you say I want to use k shingle, k equal to 2 shingles to represent this web page, what you are actually doing is take this string and you take AB, and then you move one character, you take BC, BC, you move one character, you take CD, DA, and BD, and you're done. What does it mean then? Well, this means your web page, instead of looking at it as one large string, now you have a set of items or shingles that can be used to represent this web page, right? This becomes its feature set. So what would be the max number of k shingles for a page of n characters? It's similar to n. I think it's n minus k plus 1, something like this. But usually we are looking at n, a really large n, right? Because your web page could be thousands of characters. So this is a large number. And your k is typically a small number because you don't want to have a really large k. If your k is 100, that means your shingle will be 100. And you want small. Okay, we're going to talk about how you decide k next. So this is usually small and plus 1 because you're at the end of the string. But if n is really large, we can ignore this. So approximately n shingles for a page of n characters. So other details about shingles. If you have white spaces in your text documents, we do not ignore them, but we will turn multiple white spaces into one, for example, like here. You have multiple ones, and you turn them into one. And this is your document 1, this is your document 2. If you look at them, they have a common nice shingle if you ignore space. If you don't ignore space, they will not have a common nice shingle, okay? So it's just, in practice, you do not ignore white spaces, but you do turn them multiple ones into one white space. So how do we decide on the shingle size? Well, if the shingle size is too small, many documents will falsely become similar. If it's too big, you might miss truly similar document. But what does it mean then? When we say too small, what would be the smallest shingle that you can use? Anybody? One character, great. So if you have shingle of size 1, what would be the set that would represent any document in English? It would be A, B, C to Z, right? And every document will have exactly this shingle, or if they have the words covering all the alphabet. So in this case, many documents will falsely become similar even if their semantics are totally different or the sentences are very different. What if you use a really big shingle? This means, like in our previous example, even if you miss one character, the two documents will not be the same. Let's look at here. Right, so if you're using a shingle of size 9, then even you have touch down and touch space down, you will say these two documents are not sharing any shingle because your shingle size is 9. However, if you use a shingle size of 4, this one will have a shingle that is touch, and we'll have another one is OUCH space, and eventually it will have another one that is down, right? And for the D2, you will have touch, you will have OUCHD, which is not the same, but eventually you're going to have down, right? So in this case, at least you have two shingles that are in common if you use K equal to 4. 1, 2, 3, sorry, yes, 5. Okay, so you don't want it to be too small, you don't want it to be too big, but how do we decide? Well, in general, if we are processing English documents and the documents are emails, you use K equal to 5. So this is empirical numbers. What you will usually do is you look at your documents, you take a small sample, you try different shingle size, then you figure out which one you like. But for email, let's say your K equal to 5 and your characters are letters, alphabet plus space, okay? Then you just remove anything else. So what would be the possible number of 5 shingles? Well, when we say 5 shingles, that means you have 1, 2, 3, 4, 5 spaces to put characters. And what are the possible characters that you can put into this space? Anybody? You have A to Z, and you have Y space right here. And what's the total number of different characters you can have here? (26 plus 1), so it's 27. So each location in a shingle, you have 27 choices, different choices. So it's 27 to the power of 5, 14 million. So the number of possible 5 shingles is 14 million. It's pretty good, large number. And let's suppose your email is n characters long. The probability of a shingle appear in the email is what? N characters. And we say approximately you are going to have n shingles, right? Given that your n is much larger than 5, so you can say I have n shingles. And what would be the probability? It's n times 1/40 million. How does this work? Well, because you say the maximum, we say the maximum number of 5 shingles in that n character document is n. So let's say from first shingle to the n shingle, we randomly pick one from your shingle pool, that's 14 million. So 14 million. Then we randomly pick one, another one, until we randomly pick the n one. For any shingle to appear in this document, just sum this up. And that's this. Okay. It's like if you're not familiar with probability, it's like the probability of drawing something, and you would be able to draw a specific thing in your large pool, and you can draw it n times. So this is good. This is much smaller than n. What does it mean? This is good. Well, because now your k is large enough so that the probability of any given shingle appear in any document is low, right? So this means if there is one shingle appear in 2 documents, we say this is not really just by chance, because by chance, the probability is low. If that shingle appear in both documents, that should mean something. But some caveats to the previous examples. Some letters space are more common than the others. So your shingles, some of them will occur more often. You may ignore less frequent ones. So maybe 20 instead of 27. What does it mean? Well, remember we are talking about 5 shingles. Oh, sorry, 5. And we are saying that every location you have 27 choices, right? So you're going to have 14 million different shingles. But in reality, when you look at emails, you don't really have something like X, Y, X, Z, C, right? It's just highly unlikely. So you can remove this. Well, remove this in your calculation. That means you ignore them, and your number of shingles might be just 20 choices times 20 choices, and so on. So it's much smaller than 14 million. All right, so that's everything I want to tell you about shingles. It's actually not very difficult. It's just one way to represent a document. But think about this. Now, let's say you have a bunch of documents. You are able to convert them from strings as a string representation to a set of shingles, and you can decide on the shingle size. And your next goal is to be able to compare the similarity between 2 documents, right? D1 and D2 and so on. And now each document is not a string anymore, it's a set of shingles. And from our example, we know that we will have a large number of shingles. So it's computational expensive to compute your Jacquard similarity. And it's also a huge storage overhead because you have to store all of them. Let's say you have millions of documents, 4K per document, that's a lot of storage. So what we want to do is to reduce your large set into smaller signatures so that we can compare them. And that's your min hash algorithm. So what does it mean then? Let's go back to the whiteboard. So now we have set the stage for min hash algorithm and your locality sensitive hashing algorithm. Just want to give you a quick recap and an overview on what we are going to talk about. So our goal is to be able to compare sets, okay? And I gave you an example of sets. It's documents. So document 0 to document 1 million minus 1, because we have 1 million document and we always start from 0. Remember we talked about this matrix? Now each document is represented by shingles. Okay, and we say if we use 5 shingles, we probably have 14 million different shingles. How do we represent shingles in the matrix? Well, easy. You just start from shingle 0, shingle 1, shingle 2 to shingle 14 million. And you say, okay, document 0, which shingle do you have? Document 0 says I have shingle number 0. I do not have shingle number 1. I do have shingle number 2. So document 1 says I do not have shingle number 0. I have 1, and so on. Okay, you get the idea. So this is how we would be able to generate this huge matrix storing all the shingles for each document. And still remember, our goal is to be able to find similar document. So to find similar document, we have to compare documents, right? We have to compare D0 to every other document. And think about comparison between these two. To compute Jaccard similarity, we need to ask, what's the intersection? Are they the same? Oh, this is the intersection, but this two counts as the union, right? And then we have to compare each items. So what is your complexity then? Well, for each similarity between D0 and D1, for example, we have to do 14 million comparisons. And to find the most similar documents to D0, we have to do D0, D1, D0, D2, and so on, right? We have to do this how many times? Roughly 1 million times, because you have 1 million documents. So 1 million times, every time you have to do 14 million, that's 14 million square, and that's a crazily huge number that we don't want to have. So min hash algorithm is going to do this. It will tell you that instead of doing this 14 million comparison here, let's just generate some smaller sets of signatures so that you don't have to compare them. Okay, you're focusing on some sets. Then locality sensitive hashing says instead of comparing everyone to yourself, let's just focus on the ones that would work. So eventually, both algorithm will help you. You compare small signature with a limited number of documents to find the most similar documents. Okay. All right. So let's go back to the slides. Min hash signatures. So min hash is a similarity preserving signature, which means, let's say we have a signature function. You just think of this as a function. This function takes input of D, which is a document, and generate the signature of D, okay? And of course, the signature will be a smaller data set than your original D. So our goal is that if your D1 and D2 are similar, two documents are similar, then their signature should be similar. But how do we decide that? Before we talk about the algorithm, let's look at this characteristic matrix of set. This is very similar to what I was talking about on the whiteboard, but this one is transposed, which means you have all the elements here. This is your 14 million shingle, and this is your document. Okay, so what does this mean? This says S1 contains A, does not contain B, does not contain C, but contain D, does not contain E. Okay, so same as S2, S3, and S4. So these are 4 sets. Universal sets are A, B, C, D, E. These are all the shingles you can have, or all the item sets you can have for any document. Okay, so how do we generate min hash signature? We call it min hashing a set. It's actually super easy. You pick a permutation of rows. You look at this. You just randomly permutate the rows, right? Remember it was A, B, C, D, E. Now it's B, E, A, D, C. The min hash signature, the signature of S is the first row where Sij is 1. What does it mean? So this is the document that you want to generate a signature, okay? And you scan from the top. 0, we don't care. 0, we don't care. Oh, A, S1. So the signature of S1 is A. The signature of S2 is we don't care, we don't care, we don't care, we don't care, and C. Signature of S3 is 1. Great. Don't have to scan further. Signature of 4 is A. Okay. Very easy. That's it. That's the entire Ming hash algorithm. Any questions? You probably don't know what to ask, because this sounds very easy, right? But one thing to note is we say we want to pick a permutation of rows, right? So if you permutate these rows again, let's say you use A, B, C, D, E as the original one, where you have the same signature or maybe different signature. Anybody? It might have different signature, right? Because what I did was I was just scanning from the top row and I found the first one and I say this is the signature. So the order does matters. So then the follow-up question would be, well, if the signature will be different every time, how good are these signatures? So how do we define how good these signatures could be? Remember from the last slide, we said this is the property we want. Oh, sorry. Yeah, this is the property we want in a signature. If two documents are similar, then their signature should be similar. Okay, so that means we want to be able to verify this to see if it still holds. So let's look at this Ming hash and Jacquard similarity. On a random permutation of rows, just like what we did, we assert that the probability of the signature of two documents to be the same, so it's important here, the signature of this document is the same as this document is the same as the Jacquard similarity between these two documents. Okay, this is super cool. That means if we want to calculate the Jacquard if this is true, that means if we want to calculate the Jacquard similarity, we don't need the entire document. We only need to look at the signature and see if they're the same. So Ming hash is a locality sensitive hash function. Normally your hash function will place similar items in every bucket, right? Like remember in your PCY. But in Ming hash, similar items, that means the items with high Jacquard similarity, the documents with high Jacquard similarity will be placed in the same buckets, right? The same buckets means their hash results are the same. If their hash results are different, that means they're in a different bucket. They will be placed in the same buckets with high probability. Okay, great. So similar items. So if Jacquard similarity is high, then the probability of these two things will be in the same buckets will be high. Okay, so looks good. But how do we know this is true? Let's look at some intuition. Consider this probability of two signatures being the same. How do we know they're the same? Well, if you are looking at only two items, okay, because we are doing item pair-wise comparison, there will be three cases. First case is both of the rows when we scan from the top to the bottom. The first case would be both items would have both documents would have a 1, right? It could be something like this. The second case is one of the document could have a 1, the other one would have a 0. Okay, so it would be like this, or maybe this, or this, right? The next case would be both has 0. Okay, three case, very easy. What does this mean? Well, if you scan from the top and you see 0, 0, when you see zero, what do? Remember when we generate a signature, we just ignore zeros, right? So if we have 2 zeros, you ignore them until you reach a 1. So if you either have 1, 0 or 0, 1, this tells you that these two documents do not have the same signature, okay? Because they don't have the same 1 at the same row. If you see a 1, 1 first, that means these two documents have the same signature. So our goal is to be able to see type X rows both once before we see any of the Y rows. 1, 1, and the other one 0, right? Do we care about Z? No, we don't care about Z, because if we have Z, we just ignore it. So the probability of seeing a type X, which implies these two signatures are the same, before seeing a type Y, which implies they are not the same, is X over X plus 1, right? Pretty straightforward. If you have many, many X compared to Y, then this number will be large. That means the probability of two documents to have the same signature will be large. So in general, we are going to hash although we just proved that the probability of two signatures being the same is the same as your Jaccard similarity, but shrinking the entire 14 million columns into one signature is not going to work. A good way to do this is we still hash it, but we hash it many, many times. So for example, if you look at this table, remember we say when we generate a signature, we would just scan from the top and use the first use the first 1. So if you look at here, the first hash function tells you that the signature for S1 is 0. Signature for S2 is 2. The signature for S3 is 1. The signature for S4 is 0, okay? Then after you create your first signature, you permutate the rows again. Remember we say after you permutate them, you have a different signature, right? Then you generate your second signature. Then you can do this many, many times, maybe 100 times. You have 100 signatures to represent an item that you want to compare. So 100 signatures might sound one too many, but compared to your original data set with 14 million sets, it's a much smaller set that you can compare. So if we look at here, this is your original row ID. You can permutate your row ID and you scan the table once to generate all the signatures with one scan of the entire matrix. And we're going to talk about this next time. That's it for today. Make sure you read your textbook, work on your assignments, help each other. All right, any questions? I do have my office hour today, so if you want to stay for the office hour, you can stay. Or I will see you on Monday with your quiz that will cover everything we taught after the last quiz. Please don't ask again on them. All right, thank you, everybody. I will see you next time.
Thank you.
How do you guys like your assignment 1? Set up the environment is harder than actual code. Yeah, that's true. Yeah, it's hard. But think about this, when you start working, people would usually give you like 1 month. If you are in a big company, right, they'll give you a 1 month tutorial to understand their environment if you work for Google. If you work in a startup, they will usually just tell you that, hey, you can SSH into this machine and start to run your code. You will be like, what? What does it mean, SSH into this machine? And how do I connect my notebook and run code on the server? You have to set up all the environment yourself. I hope this experience help you to be able to find answers and debug the error messages very quickly next time. All right. Anybody wants to ask questions about the office hours?
Yes, wait a minute.
Sure. If you think assignment 1 is difficult, please start your assignment 2 early. And if you want, post study sessions on Piazza so that people can come and help each other. As long as you don't share your code, we are good. All right, I got a question. Explain slides P28. Let me find slide P28. Oh, because our goal is to find the probability. Our goal is to do this. We want to be able to calculate the probability of 2 signatures being the same, right? 2 signatures from 2 documents, SI and SJ. And think about how we generate the signatures. We start by looking at the first row and we scan through the entire table, right? And when we generate signature, we just ignore zeros. So if you have 0, 0, we ignore them. So we don't have to care about this. So both zeros, no. And think about 2 documents. What would be the case when you do have this 2 signatures are the same? The only time that you will be able to achieve this is you see a row where 2 documents have a 1 before you see any of these rows. Okay, so that means you want to be, for S1 and S4, sorry, S3 and S4 to be the same, you want to see this row before you see this, or this, or this, or this, right? So what would be the probability of seeing this before everything? That would be 1 over 1, 2, 3, 4, 5. Right. So the probability of S3 signature is the same as S4 signature is 1 over 5. Because you can randomly permutate all these rows. Did I answer the question?
Hello, Professor.
Yes.
Yeah, my first question is just for maybe it's the page 25. So for the sequence are the sequence is the sequence random? Like before it's from A to E, and then it changed the sequence of the alphabet. Is the sequence randomly?
Sorry, which one? Which?
Yeah,
Which- this
all
one?
the elements. Yeah, before elements is from the first one is A and B and C and D and E, and then now it becomes B, E, A, D,
Yeah,
C.
it's a random permutation.
Randomly. Okay.
It's a
got it.
random permutation.
Okay.
We're going to talk about this next time.
Okay. But you said it will include in the quiz, so I'm afraid about that.
Well, you shouldn't be afraid about the quiz, right? It's
Yeah,
good that you asked the question. It's random.
Okay. And the next one is about the SON algorithm. So the SON algorithm is that we divide a very large file into pieces, and we calculate the free item size piece by piece. And so in this algorithm, do we need to consider about the false positive or false negative, or this algorithm can ignore or can eliminate those?
Some algorithm will not have false positive and will not have false negatives.
Sorry, pardon?
It will not have false positives
Oh,
or
okay.
false negatives.
Okay.
But that shouldn't be the answer you are asking. You should understand why it does not generate false positives and false negatives.
Just like because if for one items, if it does not disappear every piece, and it certainly not be the frequent item set. I only know about that.
Right. So that's false negative, right?
Yeah,
That
that's
means
false
you
negative,
eliminate
yeah.
false negatives.
Yeah.
And how do you eliminate false positives?
I don't know how to eliminate false positive.
Okay. Read it again. But in general, you are going to the algorithm do a second pass and eliminate the false positives, right? Remember this map reduce, you have two passes.
Oh yeah, yes. Let me check. This is a MapReduce part. I guess, yeah.
Right. So what's the question?
Yeah, how to eliminate the false positive?
If you look at the second pass,
is that second pass? Or this one?
this one.
Okay.
Right, it counts the candidates again.
Yes.
So that's how it removes false positives.
Oh, okay, got it. Oh, just I calculate again, and then we can. Oh, okay, got it. Thank you very much.
Sure.
But just for the first step, it remove the false negative, and for the second step, move the false positive.
Right.
Okay, got it. Thanks. Okay, one more question. So in the second assignment, you said if we implement the FP pass, right, by ourselves, this bonus will this bonus be added to the whole score or just for assignment 2?
Assignment 2.
So not like Scala bonus, right?
Scala bonus is 10%, I think.
I mean, if we do Scala and the bonus will be added to the total score for the whole semester, right?
Yeah, but if you add to the assignment 2, assignment 2 will add to the total score of the entire semester.
Oh,
so
oh, got it. So the FP bonus is same as Scala bonus, right?
right, but it's just,
Okay.
it's not a percentage.
Okay, got it. Thank you. Okay, that's it. Thank you, Professor.
Sure. All right. Anybody?
Hi, Professor.
Yes.
Can you lead me through the step 2, the frequent item set generation of the FP3 algorithm?
Okay, which part?
We can starting from the generating the pattern base. Like I understand these steps, but what are our final results?
Okay, let me see. You understand how to generate all these conditional frequent pattern trees, right?
Yes, I think I understand those numbers and the content in the set, but what are our final results? Is the frequent pattern our final result?
Here.
But yeah, and what about the singleton cases? Are those single? So this whole chart are the
right,
final
the entire
result.
table, right?
Okay.
But remember, when you generate frequent patterns, what is your goal? What is your ultimate goal? Your goal is to generate the association rules, right?
Yeah.
And single items doesn't really help you to generate association rules. That's why the patterns on the right will be able to generate association rules. In general, people like the one on the right and ignore the single items.
Okay. So we have talked about how to find the frequent items, but did we cover actually generating the association rule?
Yeah. Wait.
So, I only think about like finding the frequent items, but
yeah, remember when I talk about this, I said you will forget what we did on all these association rules because we will only talk about them at the beginning. And
yeah.
We are going to focus, because this is not difficult, right? These association rules, the reason why this is generating them is not difficult because you only have a few of them that you have to process, a few of the frequent item sets. So the real challenge here is to identify frequent item sets. This is how you generate the rules.
So we have the frequent item set and
think we did a quiz on this already, right?
Yeah, but
yes,
I don't remember. Oh, it reminds me of it. Yeah,
it's okay.
Thank you.
We can do a quiz next
I totally
time.
forgot about it.
No, this is very important. This is very, very important because your goal is to generate.
Yeah, I know. This is our final goal, but I actually forgot about it.
Yeah.
I will see this part again. Okay, thank you.
Okay. You are welcome. All right. Any more questions, guys?
Yes. So like for the FP path, we draw this path from the ordered item set. Like the first one is KEMOY. What about we draw first from KEO? Will it generate the same
Yeah.
graph?
It would be the same tree.
Okay, so we can ignore the orders.
That's correct.
Okay, got it. So generally, all the algorithms like PCY or SON just supported for the calculate the free item set, but our ultimate goal is to get the associated rules, right?
Right. That's
Okay.
true.
Thank you very much.
Sure.
Hi, Professor.
Yes.
Can you go to the conditional frequent pattern tree again? I'm wondering how, besides we create the solid line here, like a try, how do we build those dotted line? Like for example, if we go from K to, you can.
Somewhere here, right?
Yeah. This will work. Like when we go from K to E to O, like this is the second time we find the O, because we have already covered KEMO
right
in the last case, and I'm wondering how I can create this dotted line. Like when I go from KE to the second O, this branch, if I want to create this dotted line,
you have to keep in your memory all the items you have inserted the last time you see that item, so that you can always create it like here.
So do I need a map data structure to remember the reference for? Yeah. Okay.
Right.
Gotcha.
So if you look at here, you don't have to track every Y. You only have to track the last Y, right?
I got you. But I still need to remember the head of this singly linked list, right?
Yes.
The first Y. Okay.
Yes. Yeah, that's a good question. I didn't cover all these tree algorithms. I think you should already know from the algorithm course to be able to build those.
Okay.
Are you going to implement it?
I don't know. This sounds really complicated. I think anything I think has something to do with tree gonna be very complicated. And
yeah,
also,
but if you can do this, you can do any tree.
Yeah, I think so. And this tree also covers recursion.
Yeah. So this is a good exercise.
I think I will try.
Good item on your resume. All right. Any more questions?
I think that will be all. Thank you very much.
All right. Thank you. Do your homework and read the textbook.
Yeah.
All right. I'll see you next week.
See you, Professor.
Bye.
Bye.